Special titrations. What that means is we're not going to do an entire chart, we're just going to do one line. What we need to do is to identify what stage we're in of what type of titration. Now remember, there's 4 types of titration: strong acid, strong base, strong acid, weak acid, strong base, and weak base, strong acid. And what I've done here is I've done 4 odd numbered problems on page 763 and 764. And I'm breaking them down as to the process you need to follow to figure out how to do this. We are looking for the pH in all of these, but the scenario is going to be different for 3 of the 4. So we need to identify what's going on here. Now, you have to remember there are 4 stages. The first stage in all of them is when you have no titrant being added. You just have whatever's being titrated. Okay? And so you just take the pH of the strong acid or strong base, or you use the quad form to figure out the pH of the weak acid or weak base. Stage 2 is when you have more acid than base, or more base than acid, depending upon what your conditions are asking for. And the reverse is stage 4. And generally, with strong acid, strong base, strong acid, it really makes no difference which one of those 2 there are. The crucial one is stage 3, which is the equivalence point. The equivalence point is where the moles of acid and the moles of base are the same. We have 2 problems that involve that. And so that will automatically be stage 3 problems and how we deal with that. So that's the preface to all of this. It sounds complicated, but if you're able to do the 4 previous titration systems, this will be much easier to do. All right, so let's start off with number 77. You're going to need your calculator handy for this, and at any point if you need to stop, please stop and make sure that you double check your calculator work and your understanding of what we've done up to that point. All right, so we've got sodium hydroxide and hydrochloric acid reacting together. So this is the basic reaction. This is a double displacement reaction, so the H and the Na are going to switch, and it's going to give you NaCl plus H2O. So there's no conjugate acid or base we have to worry about for strong acid, strong base, or strong base, strong acid. And which one we pick makes no difference. You're going to get the same value regardless. So let's take a look at this. Let's start off with the volume of the acid. The volume of the acid is 25 milliliters, which becomes 0.025 liters. The moles of HCl, your acid, is 0.025 times 0.1 mole per liter. The liters cancel out and you get 0.0025 moles of HCl. So that's your acid, 0.0025. Your volume of base is 15 milliliters, so that becomes 0.015 liters. We take 0.015 liters and multiply by 0.10 moles per liter, we get 0.0015 moles. Okay? So this is either stage 2 if you are going to do acid-base. If it's a stage 4, if you do base acid for the strongs, again, it makes no difference. The total volumes of some of these 2 volumes right here, which is 0.04 liters. The moles of excess. Well, let's take a look at the moles. We got 0.0025 here, 0.0015 here. We obviously have more acid than we have base, so we're going to subtract the 0.0015 from the 0.0025, and we get 0.001 moles of. And this is where it's important you put in the fact that you have more acid, and because of the strong acid, you're looking at the hydrogen ion concentration. The next thing you're going to do is you're going to take 0.001 divided by 0.04. And I get 0.025 moles per liter. And since this is moles per liter, and since this is hydrogen ions here are acidic, That's going to be H positive. So the pH then is going to be the negative log of 0.025. And your answer turns out to be 1.60. Okay? All right. Let's move on to the next problem. Number